Okay, so we are live now. Let me share my screen. Okay, but first of all, I have to. Okay, okay. Let me share my screen. Let's start with our discussion, our today's quiz solutions. I will quickly show it and then I will share it with you that you can go through the details of it. I think the questions were straightforward, but let me just discuss. Okay, so this was quiz 2. First question, okay, dice was rolled many times. So the basic understanding here is, let me use. Just a minute, let me open my OneNote where I can write. So basically this question is, you want to find expectation of e to the power x. So simple way to compute from the observations from the samples is that you find e to the power x for each sample and just take the average. Like this expectation value is just the average. So you have to average of e to the power 2, basically e to the power 2 plus e to the power 5 plus e to the power 1, so on, divide by total number of observations, which is 7 in this case. So this is the thing, np dot exponential of every term, and you sum them up and divide by 7. So that's the solution. If you have any questions, you can ask. I will just turn on the. Oh, I'm sorry. My share screen turned off. Okay, so let me turn on the chat so that if you have any questions, you can type on the chat window. Okay, so the next question is you have to estimate e to the power log x with this sequential estimation. So basically, expected value at a particular time instant t will be simply log of pt upon capital T, where pt is xt times p of t minus 1. So the basic thing is you have sorry. Okay, so basically you have it's causing some problem. Oops. Oops. Sorry. Yeah, you have the samples. So your expected value will be expected value of ln x for these samples will be simply ln of S1 plus ln of S2 plus so on up to ln of ST divided by capital T. So what is ln of S1 plus S2? It's S1 into S2 into so on up to divided by capital T. So basically you want to save the product of all these numbers. This is product till ST and divide by the number of samples. So product of samples and number of samples. Next is, okay, given it drawn, find the maximum likelihood. Oh, this was little, you have to think from the basics. What is the meaning of likelihood? Likelihood is basically probability of observing all these observations. So what is the probability of observing this sequence? So basically probability of observing 2 times probability of observing 1, because these are all independent. So the joint distribution, joint probability can be broken up into individual probabilities. So what is probability of 2? It is a. Probability of 1, it is a. Like that, you 5 times 1, 3 times 2, and 2 times 3. That is the likelihood. Now you want to maximize this. That is a simple thing. Just differentiate and make it equal to 0. Next is find. So basically this was a transformation of variables. These are discrete variables. So py equal to 1 will correspond to x equal to -1 and +1. Just add up those two probabilities and that's the answer. X equal to 1 and x equal to -1. But here this is a continuous random variable. So simply adding up does not work because you have to make sure that the area under the curve is also 1. So to derive the curve, you know the formula that you divide by the Jacobian, determinant of the Jacobian. So basically p of x times 1 upon derivative of py by px means py by px and the determinant of that is the number. So you get 1 upon 6 under root y is 1 in this case, so 1 upon 6 is the answer. Next you have this is simple. Pardon?
So in the previous question, I took it as to mean the probability instead of the PDF because it was not clearly specified. I thought that it was find probability that y is equal to 1, and hence I did none of these because y cannot be 1 because it's
No, we are using p for PDF, right?
Yeah, sir, but it was a little ambiguous for me.
Okay, but we were very consistent with the definition. With the definition of p means we always use p for PDF. Right here also you see p of x is the PDF, uniform distribution. Another random
But for
variable
probability also we will be using p only, right?
means probability mass function.
No, like probability of an event.
For continuous random variable, we never talk of probability because we know it is 0 because it's continuous random variable.
Yeah, sir, but
I think we have been very consistent with the definition of p. Only for discrete random variables, p of x means the PMF, probability mass function. But for continuous random variables, it is always the PDF. Because the probability in a continuous random variable, probability of observing a single value will always be 0 unless it is a delta function. Means, so that is, I think we are very consistent with this notation. Okay, so number 6. Okay, so for this, okay, I can't help here. I think we have been very consistent with P. Okay, number 6, scalar data, clustering. Basically, there are two clusters. So if you 1 and 3, so see which points are nearest to 1, they will go to this cluster. Which points are nearest to 3, they will get to the other cluster. Again, compute the means of the new clusters, and these are the new means. So 1.4 and 1.2 go into one cluster, and the other 3 points go to the second cluster. Find their means again. These are the new means, new centroids. Then we come to, so this was a KL divergence. You find P of A of X, basically X can take 3 values, red, green, blue. And you find probability of A for X equal to red is how much? 1 upon 8. Like that, you compute. So 1 upon 8 times in PB it is 4 upon 8. So which means 1 upon 2. So in this way you compute KL divergence is simply what do you say? Px times log of px upon qx, summation over all x. Okay, then we have length and width. We have to apply PCA. Basically, you normalize it. So basically, subtract the mean normalization, and then take x transpose dot x.
Sir, in the last question, you didn't actually take in the factor of 1 by n. In covariance matrix, we take in the factor of 1 by n to multiply all the values. I have referenced the slides also in the PCA, and you have incorporated a factor of 1 by n in the slides also.
Oh, really? Okay. Okay, my mistake then. Okay, then the answer will be none of these. Basically, you mean to say that it should be divided by 3.
Yes.
Yes, sir.
Yeah, I think this is my mistake. Okay, so none of these is the answer here.
Thank you, sir.
Okay, thank you.
Thank you.
Hello, sir.
Yeah.
So I saw the denominator. I mean, all the parts were same. Like all the elements were same in my case also. So I corrected the 0.5, 0.5, 0.5, 0.5 wala answer. Like I did not consider the none of these. But my answer was divided by 3. But I take the correct answer as uh, told by you. Like
Mhm.
the fifth
Okay,
one.
so means this is a solution which I prepared. Okay, and you are. I think none of these is the correct answer, if because I also missed the 1/3 factor. But I think the right answer should be none of these. So all those who have marked it as none of these, they will get full marks.
But sir, all it was like I did not see the 1/3 part, and my answer was also matching 0.5, 0.5 like that.
Mhm.
So was it wrong?
Now it is wrong because we have to divide by n also. Yeah.
Okay, sir.
So next question is about CNNs. This is very simple computation. You know the formula means n minus f plus 2p divided by strides plus 1, like that. So you compute it twice. Stride was 2 here, stride is 1 here. And
Sir,
that's, pardon?
sir,
Yeah,
about the last question.
this one.
Yes, sir. In somewhere in the slides also, sir, you have mentioned that we can ignore that 1 by n also.
Okay, I will
Somewhere,
let me see the slides. I don't remember exactly.
sir,
Which one was it?
maybe that in the CNN slides part, in the video lecture, you have taught about that when we have classification, how to apply PCA in a classifier, and you have not uploaded the slides for that part. Maybe in that it is, you have mentioned that 1 by n, it is not necessary to take 1 by n.
I said 1
I
upon n.
don't remember correctly, but that might be due to you might be doing some derivative and equating it to 0. Then the factor might not be that worth. But here we should incorporate
Yeah,
that.
but the definition of S includes 1 upon n.
Yes, sir. In this pca.20.pca.pdf only on slide number 17.
Okay, I'm trying to get to the slides, but it is taking some time. Okay, we will come back to this, but yeah, as far as I remember, 1 upon n should be there. Okay, then this next question is same formula. Basically, you have to find the value of p. Answer is 5. That's it. Okay, that's it. So what is MTA?
Sir, marks to all.
Marks to all for which question?
The last one that that is confusing for 1 by n factor.
There is no confusion there. It's very clear. 1 upon n should be there.
Okay, thank you, sir.
Okay. Yeah, so let's come to PCA. Yeah, S is the variance matrix. It includes 1 upon n here. So 1 upon 3 has to be there. Okay, so I think answer should be none of these. Okay. Let's start with our next discussion on hidden Markov models. Yesterday, in the last class, we were discussing about Markov models, and I gave you examples many examples regarding Markov models. Let us today discuss one concrete example and some mathematics of Markov models. I will be just writing on this board so that I can be more interactive. Okay, so let's come to hidden Markov models. Let me try to first recap with an example. Let's say there are 4 seasons. Let us take the example of seasons. There are 4 seasons. Oh, the system is working very slowly. I should turn off some of the applications. Okay, we have 4 seasons. So my hidden variable will be a season, and it should be a discrete variable, right? I don't know why it is moving so slow. Okay, there is a question on the chat board. Can we get the responses? So everybody has individual responses. So I don't know how we can share, because then this means you have to share with each one of you individually. So that is not very efficient, because Mookit does not have a facility to do that. I think the best will be, if you have questions, I don't know how to do that, because I don't want to ask the TAs to send individually to everybody their responses. That will be very tedious, right? I don't know why my pen is working very slow. I have to turn off some applications probably. We have 4 seasons. Z basically is a discrete random variable. I don't know why my pen is working very slow. Let me try to turn off some applications. Just give me a second. I'm turning off all the applications which are heating up the system. Yeah, now it's a little better. Share screen. Okay. So we have got 4 seasons. So Z can take 4 values, and it can basically, Z is a random variable which can take 4 values. And now we have temperature. Our temperature is observable. This is a hidden variable. 4 seasons, and T is the temperature, which is an observed variable. So now for a particular time instant, I can have some ZT. Let's say today, let's say at time T, I have some season. And if I know the season, I know the temperature. Let me call it as X instead of T to be consistent with our notations. And this ZT, I model it as dependent on ZT minus 1. And this ZT minus 1 is in turn, it's a hidden Markov model. It's a first order Markov chain. Yeah, so this is the thing. So how do I model the joint PDF? The joint PDF probability of all the random variables, xt minus 1, z t minus 1, so on. How do I model this joint PDF? This joint PDF is a very powerful thing. Basically, it tells us how things are. Let us start with, so anybody would like to say on the chat window, how shall we model this? Anybody would like to tell on the chat window? Nobody's answering. Okay, let me write. So you have P of xt given zt, right? Because if you know zt, nothing else is required. Then start from the leaves, basically. You can also start from the root or the leaves. I'm starting from this end. But P of zt depends on zt minus 1. P of xt minus 1 depends only on zt minus 1. P of zt minus 1 depends only on zt minus 2. And in this way. Now you see this probability. Now X is a continuous random variable, right? This is a continuous random variable and this is a discrete random variable. Now I can say P of xt given zt. If I know which season it is, let us say it is summer season. I'm just giving one example scenario. My temperature, let's say daytime temperature will be, I can model it as Gaussian. It is not Gaussian, but I'm just modeling it as Gaussian with the mean in summers. What do you expect? 40 degrees Celsius. Let's say this is temperature in degrees Celsius. 40 degrees Celsius. In winters, what do you expect? Let's say 15 degrees Celsius. And like that. Likewise, other temperatures also can be Gaussians. 15 or 10, let's say winters are more severe, 10. This is winters. This is summers. Let us take only 2 seasons actually. Instead of 4, let me take only 2 seasons, 2 extreme seasons, winters and summers. Now, if I'm observing, let's say if I'm observing a temperature of 38 degrees Celsius. So probability that xt is 38. Then, so okay, well, okay, if it is given, sorry. If this is given, what is the probability that what weather it is? How will you find it out? If the temperature is 38 degrees Celsius, what is the season it is? What season it is? Let's say the sigma is 5 in both cases. Just an assumption. Okay, can you tell? So how will I compute this? I will say P of xt given z into p of zt divided by the normalizing term p of xt. So how will I compute it? I will say zt can take two values, summers or winters. So probability of zt equal to summers given this thing is equal to probability of 38 degrees Celsius given it is summer. It is like normal 38 where the mean is 40, sigma is 5 times probability of, let's say these are equiprobable, both the seasons are equiprobable, divided by p of xt. And similarly, p of zt equal to winters given this xt is 38. This is equal to normal 38 given, now for winters the mean is 10 comma 5, and let's say prior probability is just 1/2 p of xt. Which one is larger value? Which one is larger value? So this is a large value because exponential of minus 2 square, right? Exponential of minus this whole square. So 2 square 4 divided by 5. While this term will be of the order of exponential 28 square minus 28 square divided by 5, which is very, very small. This term will become very, very small, right? Because a large number in exponential of negative. So this is almost 0 and this is almost 1. I mean, if you divide by the normalizing term, this p of xt. So are you able to get a feel of it, that what is the meaning of HMMs? But I'm not studied HMMs yet. This is just conditional probability for this case. Now HMMs are, let's come this side. So there are two kinds of terms involved here. One is the transition probability. The other is the emission probability. So just now you saw this normalized PDF, this normal PDF. This is the emission probability. We have assumed that given the season, my distribution of X is some continuous PDF, let's say Gaussian PDF. But so all these terms, this one, they are all emission probabilities. Basically, given the discrete variable, what is the continuous variable? Given the season, what is the temperature? These are my emission probabilities. Right? And on the other hand, these are probability of, what is the probability that today is summer given yesterday was summers? Large probability, right? What is the probability today is summers given yesterday was winters? Small probability, because that jump will happen only once in a year. Okay. Can you tell me what should be the values here? I've already given you a hint. So what should I take my values of? These are my transition probabilities. These are my emission probabilities. Tell me, how will you model in terms of seasons? What should be my p zt given zt minus 1? Sorry. P of zt given zt minus 1. So let's say if it will be a matrix, right? Let's say this is zt. And this is zt minus 1. Zt is summer, winter, summer, winter. So how will you initialize your values? Or what should be your guess of these values of p zt given zt minus 1? Maximum for S when S, and for W when winter. So tell me numbers. Diagonal elements are large, but yes, how large? Okay. So how will you go about this? This is a very simple problem, but very basic question. But how will you think about it? How will you go about it? So first of all, you should know, given zt minus 1, what is zt? So okay. So you have to know the sequence. So let's say today is 1st of Jan. Today is winters. And this winters will continue until, let's say, 1st of June, when suddenly the summers start. I'm just taking a very extreme model. It has only 2 states. Okay, summer given summer is 0.9. Okay, why 0.9? Okay, so I will give you more principled way to assume. Your guess is right that it will be a small value or large. Summer given summer is a large value. Winter given summer is a small value. But how small or how large? How will you guess? You guess from the data. So then the summers will start. No, not 1st June. Let's say 1st May. I think 1st June is too late. Let's say 1st May, the summers start. And it will continue summers until what date? Until what date will it continue? When does winter start again? November? Okay, 1st November. Okay. 1st November, again the winter starts. Okay, this is my observation data. From this observation, can you now compute PZT given ZT minus 1? From these observations, can you compute? Let me see who computes. Just an anonymous exam. I just want to see if you are able to think. What is PZT given ZT minus 1? I have given you the observations. No answer? Any guess? Any guesses? Okay. Okay, let's find out how many days are there from 1st of Jan to 1st of May. So how many months? January, February, March, April. 4 months, right? Let's say 4 into 30, 120 days. Plus minus 1, I think, yeah. So it's 120 days. So these are 120 days. And then May to November, how many days? May, June, July, August, September, October, November. So 6 months. 6 months means 6 into 30, 180 days approximately. And then winters to November, December, 2 months. So 2 into 30, 60 days. So we have ended up with how many? 360. Okay, we are short of 5 days. That is all right. Just ignore those or add them here, something. Okay, so this is our observation. Now, can you tell me what should be the values of PZT given ZT minus 1? Okay, there's a game. I forgot the name. There's a game where the quizmaster, he keeps telling more and more hints until somebody guesses the right answer, and then whoever guesses it first, they are the winner. Anybody knows the name of the game? So the quizmaster will keep telling more and more hints until somebody guesses the right answer. So okay, this game became famous in AI until IBM made an algorithm to beat humans. So it's called Jeopardy. Jeopardy is a game where okay, something like this, what we are doing. Okay, tell me now what is so okay, let us do this analysis. For this observation, PZT minus 1 here is winters, PZT is winters. Okay, so I have 4 cases possible. ZT minus 1 is winters, ZT is winters, ZT minus 1 is winters, ZT is summers. ZT minus 1 is summer, ZT is winters, ZT minus 1 is summer, ZT is summers. 4 possibilities are there. Let us try to extract these 4 possibilities from here. This is the first possibility. Okay, let me write it down here. ZT minus 1, ZT. This is the count. So 4 possibilities. It is summer, this is summer, this is summer, this is winters, this is winters, this is summers, this is winters, this is winters. 4 possibilities. So this is ZT is winter, ZT minus 1 is winter. So plus 1 for this case. How many such cases will be there? Up till here, 120 cases, right? But here there is a boundary. Previous one was winters. Okay. So we have 120 cases. Then comes a jump. Summer given winters. So today is summers, yesterday was winters. So plus 1 here, right? This pair. Can you guess these 2 entries now? Could you guess these 2 entries now? Nobody? Okay, what is S comma S? Okay, tell what is S comma W? Yeah, we will normalize at the end, but just tell me the counts first. 1, yes. So it is 1. Now, next is summer given summer. So what is summer given summer? So from this data, summer given summer, how many are there? 180. Do it a little more carefully. It's 179, yes, because this one is excluded, right? So only up till this, you'll get 179. Okay, so 179 here. Now this jump, winters given summer, 1 case. And then remaining, there are 65 here. So how many cases will be formed? 64 cases, right? 64 cases here. So plus 64. So these are our data. Now, but what is this data? Now, if I say this is probability of summer given summer, probability of summer, comma summer, this will be 179 divided by everything. Let's say 16. How many? 365? 365. I think it is 365, right? Yes, this is 365. But we want to compute P of S given S. How will I compute this? P of S given S. So what I get from this table is P of S comma S. So ZT minus 1 is S, ZT is S. This is ZT minus 1 and this is ZT. Summer comma summer. But what about summer given summer? This will be P of S comma S divided by P of S. Anybody can tell what is P of S? Anybody can tell what is P of S, which means P of, so this is P of ZT minus 1. Basically, this is probability of ZT minus 1 is equal to summers. This is equal to how much? Now just tell me this value. Okay, you're telling 180 upon 365. Is that the answer you're trying to say? Yes. So from this series of observations, if I just consider this random variable ZT, then or ZT minus 1. So there are 180 observations which are corresponding to summer. So divide by 180. So basically this is 180 upon 165, 365. Okay, so if I put these values here, so this I get is 179 upon 180, which is pretty large value, right? Almost close to 1. And what is probability of winters given summer? This will be probability of winter comma summer. Winter comma summer is, this is ZT, this is ZT minus 1. What is probability of winter comma summer? So what is ZT? What is the numerator? Numerator, somebody saying, no, please tell the numerator. Winter, summer. So this is 1 basically, 1 upon 365. And this is 180 upon 365. Actually, you can also find it by subtracting. So basically, this is 1 minus probability of summer given summer, right? So these are the answers. Similarly, you can compute for winter given winters and winter given summers. Same way you can compute. Okay. So these are transition probabilities when you make transitions. But now let's come back to hidden Markov model. So we have two kinds of probabilities. These transition probabilities. Oh, I made it with the wrong color. Anyways, so the transition probabilities are all computed, and the emission probabilities. Basically, if you know the season today and the temperature today, then you can compute very easily. So let's say if I give you the entire time series data, let's say the temperatures. So on this day, 1st of Jan, the temperature was 20. Let's say the maximum temperature of the day was 20. Here the maximum temperature of the day was 15. Here it was something 14 something. And in this way, you kept on observing some things until the summers came. The temperature rose to 35 and then 36. Like that, it kept on increasing. So you are given this data. These are your observations of seasons. These are your observations of temperature. From here, you want to find out this joint PDF. So now, given this data, can you compute the emission probabilities? Compute the emission probabilities. Let me say emission probability is green in color. Find out emission probability of X T given ZT is summers and probability of XT given ZT is winters. How will you compute? How will you compute? Okay, so simple answer is if I know ZT, I don't need what is the season on other days. If I know ZT and I know XT, that is it. So now to compute this summer thing, I will take all the days when it was summer, all these 180 days when it was summers, and I will use this data only to compute this PDF. Very simple, right? There are 180 days. From these 180 days temperature, I want to compute the PDF. I think you have all done ML estimation. How do you estimate the mean and the standard deviation of the Gaussian PDF from the data? So this will be simply, this is equal to normal xt given mu is the mean of all these 180 values, right? 35 plus 36 plus so on, divided by 180, right? So your mu hat of summers, comma, sigma, which also you can compute, sigma hat of summers. You know how to compute this from MLE estimation, right? Now let's come to winters. Same process will follow. Take all the days when it is winters and find out the mean and standard deviation given mu hat of winters and sigma hat of winters. If you know today is winter, this is the winter, then just use these temperatures to compute your PDF. I think it's pretty simple, right? So in this way, you have computed the hyperparameters of your model. Okay, tell me quickly how many hyperparameters are there for this model? How many tunable hyperparameters were there for this model? Tell me, let's see who tells first. for this model, how many hyperparameters are there? Quickly, quickly, quickly. Okay, tell me how many parameters are there? Not hyperparameters, parameters are there. Nobody's answering. What's happening? Just for your information, we have just now seen the way how to estimate the values of those parameters. Okay, so we have one answer from Sumit. He says 4. Anybody else with any other answer? How many total number of parameters in this entire model, in this entire HMM model, which we just now saw? Saksham says 4. Shivam says, can you specify? Oh, sorry, it is different. Okay. Is it 8? Okay. I think this question we should give in the quiz. It's a very simple question, but just that it makes you think. Okay, so let's find out. This mu summers is one hyperparameter, is one parameter. Sigma is one parameter. Basically, to know, to specify this joint PDF, how many parameters are required? I need to know the mean and standard deviation, if I am assuming this as a Gaussian, right? For each of the discrete cases. So there are 2 discrete cases. So there are 4 of these here. 4 for the emission probability. And plus for the transition probability. How many are there? For transition probability, how many parameters are there? For transition probability. For transition probability, how many parameters are there? Let's see who can answer. 3. Okay. Two. Okay. Yeah, I think 2 is the right answer. You have somewhere. This thing. Okay. Yes. So we need 2 parameters. 2 parameters for the transition probability. So I was expecting this answer from you. So why 2 parameters? Somebody can say there are 4 parameters required, but you know that 2 of these sum up to 1 because the conditional probabilities, P of S given S and P of W given S, they will sum up to 1. So basically it's only 1 parameter. Other one can be derived from that. So there are 2, one for summers, one for winters. Okay, is that clear? Now, if this is a time series which has a finite starting point, then at the very beginning, we have no transition. Let's say the year starts here and there is no transition. Let's say I don't know what was on 31st December. I don't know whether it was summers or winters. My day is starting from here. Let's come to this position. Let's come to here. P of ZT given XT, P of ZT is here. I don't know what is P of ZT given ZT minus 1. Basically, I want to initialize my time series, right? So I need my initial state probabilities, whether it is summers or winters, right? If you see this, so if it has a finite starting point, let's say x0 comma z0, right? Then this will ultimately become multiplied by p of x0 given z0 times p of z0, right? This is emission probability, this is clear. But what is p of z0? P of z0 is a different thing. It is called the I forgot the name exactly. Maybe it's initial probability or state initial probability. I'm forgetting the name. It's denoted by a symbol of pi. So initial probability. So that also you need. Basically, whether in the beginning it is summers or winters. The very first observation, it's a summers or winters at the beginning of your chain. So how many parameters this will add up to? This will make one more parameter. Yes, good. Plus 1 for the initial probability. Okay, so total this whole model will have 7 parameters. We saw 6 of them earlier. One is the initial probability. Okay, so this is a hidden Markov model. Now, there are many things involved. I have given you one example. Using this example, you can understand all other things. Let's say, okay, so now the question is, this was easy because we know exactly we know the entire time series data. We know the observations. We also know the hidden states, right? But what if we do not know the hidden states? We only have the observations. So this was the first problem. We know xt comma zt for all t, right? But another problem could be, I don't know zt. We only know xt for all t, not zt. Can you now use hidden Markov models? Can you still use hidden Markov models? The answer is yes. We can still use hidden Markov models. If we know the order of zt, we may not know the starting and ending points, let's say, but I know the order. Okay, summers will come, then winters will come in 1 year. And then summer can come, then winter can come, but okay, summers will come only once in a year. So basically the transition from summer to winter will be only once in a year, and winter to summer will also be only once in a year. If I know that, that helps me to make it more concrete. I think we are already, it's 4 o'clock, we can stop here. But I think go through the lecture notes, and this example should help you to kind of nail the concept. And from here, you try to derive other things. Let's say Fitterby algorithm, how do you deal with that? So that will be helpful. And if you want, we can discuss this topic further in the next discussion also. And so, okay, maybe now a couple of logistical announcements. I will just stop sharing and stop streaming.